Hi everyone. In this video lecture we are going to discuss the most practical circuit of the Tesla coil. We are going to discuss from scratch, from our basic concepts to the practical knowledge, that how you can build up the Tesla coil circuit, the working of the Tesla coil circuit in detail, and the working of each and every component of the Tesla coil experiment circuit. This is going to be a very important lecture for those people who are crazy for the high voltage engineering. So as we have also discussed the basics of the Tesla coil, and we have discussed the basic circuit in our previous video lecture. In this video lecture, here we have the most practical circuit. Now let's start one by one analyzing this circuit and the detailed understanding. So here you have a transformer, and this is an air core transformer. These you can see here, you have two inductors, the primary inductor and the secondary inductor, and these are actually inductor, and they are placed near to each other so that there will be the mutual inductance, there will be obviously the flux linkage between these two inductors. Let's represent it by M, that is the mutual inductance. So the primary side inductor typically have around 10 to 20 turns, while the secondary side inductor has around 1000 to 1500 turns. And this is an oil immersed, and these inductors, and obviously as I told you that they are air core inductors. So since these are air core inductors, so we can say that this is an air core transformer. And why it is an air core transformer, why it is not the iron core transformer? Well, this is another question which is being asked in several interviews. This is an air core transformer because this transformer will be working at a very high frequency, at a frequency ranging from kilohertz to megahertz. So this transformer is operating at a high frequency. That's why its size is small and it is air cored. Well, these inductors are oil immersed. They are oil immersed. Why we immerse them in oil? Because of the cooling. So we want the proper cooling of these inductors. Okay, so as I told you the number of turns, and here you have the two capacitors C1 and C2, and these are actually high voltage capacitors. And this is what? This is a ring like structure. It is a metallic ring. The metallic ring also behaves like a capacitor. It is also known as torus, the torus ring. It is in the shape of the toroid. Okay, so this is the primary side, this is the secondary side. This is the circuit of the Tesla coil. What's behind here is that we have an AC supply. Okay, in our previous lecture video, what we did, we had a spark gap here, and we connected an AC supply here, and that was a theoretical circuit. And although that circuit also works practically, but had several limitations, as I explained you in the previous lecture video. So that's why practically we don't have such type of an arrangement. We don't have a spark gap here, but rather what we have here is the we have this arrangement. Let's see here, you have an AC supply, then you have a full bridge rectifier, and as you know that the full bridge rectifier converts the AC into the DC voltage level, but then we have the capacitors arranged in such a way that we get a positive DC supply and the negative DC supply. Don't worry, we are going to study in detail what's here and what is here. And then we have a gate driver circuit. What is gate driver circuitry we are going to use here, and how it will be working, we will also be covering in this video lecture. Then you have IGBTs, and what you do, these IGBTs and these capacitors you are used to supply the voltage here. Now we will be studying how what will be the waveform on the primary side and what will be the waveform on the secondary side. Before we proceed on further, first let us understand this secondary side. So this is the capacitor, and this is the this also behaves the capacitor. This is like an electrode. So for a moment I am going to neglect this, because this is just used to spread the arcs in the surrounding environment, that electrode. So we are going to ignore this for a moment, and first let's understand what's happening on the secondary side. So I am also removing this for a moment, because I want to explain what's going on here on the secondary side. So what we are left with, the capacitor and an inductor. And you know from your basic knowledge that if you have, let's say if you have a charged capacitor here, what happens, this capacitor and inductor, they continue to exchange energies between them, and this is like a circuit which is also known as the tank circuit. Tank circuit is a circuit in which you have inductors and capacitors, or you can say different types of energy storage elements which continue to exchange their energies with each other. So so you have a capacitor and inductor in this experiment which are connected in parallel. As you know that when these capacitors and inductor are in parallel, they resonate, they exchange their energy. They start exchanging their energy when they resonate, because or at the resonant frequency, what happens, the circuit impedance is just equal to resistance only, because the inductive reactance and the capacitive reactance, they become equal to each other and they cancel each other. Now what is that resonant frequency, or you can see that the oscillation frequency is given by a simple formula by equating them. It is equal to 1. I think this is not clear to you. Let me write it below. The oscillation frequency of the circuit in which you have capacitor and inductor in parallel to each other is 1 divided by 2 pi under root L C. L is the inductor and C is the capacitance. Now what happens at resonant? As you know that every physical thing stores energy in it. All you need is to resonate it. As you have seen that if you have this type of glass at the resonating sound wave, what happens? This glass breaks up. Similarly, you have this type of circuit, and all you need is to hit this, this inductor and capacitor LC circuit with their resonant frequency. If you are able to hit this inductor capacitor circuit with the frequency which is equal to the resonant frequency, what happens? The stored energy behaves in such a way, or the energy transfer from primary to secondary side is such a way that the output voltage, that we get the maximum possible output voltage, that is, it starts from the peak and then damps out. So such type of waveform is achieved if you hit this inductor and capacitor with the frequency which is equal to their resonant frequency. How this happens, why this happens, because you know that this capacitor opposes the change in voltage across it and inductor opposes the change in current across it. So, how you are able to get this type of waveform? Let us see here. I am going to draw the core concept, that how you are able to get this type of waveform. Okay, first let us say that let me remove this as well. Okay. So, what we have here, let us see this waveform. Let us say at start, this is the capacitor voltage, which is the maximum. Now, what capacitor wants? Capacitor doesn't want the voltage across it or the change in, because once you have hit this circuit with the wave after the mutual inductance, because here you have the primary side as well. So, the capacitor is first fully charged. Now, what happens? The capacitor voltage is here across this inductor. Now, capacitor wants to discharge, but that is, it wants inductor to allow that the current must flow through it, but inductor doesn't want to it will not allow the capacitor, but eventually what happens, the capacitor voltage is decreasing in this way. Okay, the capacitor voltage is decreasing. So, what's happening is that inductor current is going to increase. Obviously, when capacitor is discharging, what happens, the current from the inductor starts and the inductor current is rising in this way. Now, this is IL waveform. The dotted waveform is representing the inductor current. Now, what happens? Now, inductor has reached the maximum current and the capacitor has discharged to the 0 voltage level. Now the inductor is charged. Now, what happens? This inductor is charged, but now this inductor wants this current to be maximum. Inductor doesn't want to and that the current decreases, but now since capacitor has no current, so in that effort, that inductor doesn't allow or it resists the change in current through it. In this effort, what happens, the inductor is trying to charge the capacitor so that it continue to get the maximum current, but inductor doesn't know that its energy will radiate in this way, but this happens. What happens next? The inductor current continues to decay, and what happens, this capacitor gets charged. Now, this capacitor is charged. Now, this capacitor doesn't want this voltage to change. Capacitor will resist that voltage. Now, capacitor know that it is being charged by an inductor. So, a capacitor will try to keep this inductor in such a way. Capacitor is willing that the current must be flowing through this inductor so that the voltage here must be maximum. In that effort, what happens? The capacitor eventually discharges across the inductor, and what happens? The inductor current has reached the peak. And what happens? There is a continuous exchange of energy between inductor and capacitor, and this waveform of the voltage across the capacitor repeats. But what happens is that at the resonating frequency, what you get? You get this waveform of the very high frequency. This waveform will be of very high frequency, but practically what happens? You have the circuit resistance. So, you get the damped sinusoidal waveform like that. Okay, this waveform you get across this capacitor. So, in effort that inductor resists the change in current and the capacitor resists the change in voltage across it, this circuit gets resonate at the resonating frequency. If you are hitting this inductor and capacitor with the proper oscillation frequency, then they will resonate, that is they will start exchanging their energy properly, and there will be the proper resonance in this circuit. So now how to achieve this resonance? Think for a moment. And what I ignored here was the torus ring, that is, and it is also known as the top load, because the voltage here is very high, that you get the high voltage sparks across the air. There is a discharge in the air. So right now, till now we have discussed the secondary side of this Tesla coil experiment. Now what's on the primary side? Because we want to hit this capacitor and inductor with the proper resonating frequency at which this circuit resonate, we have to supply that frequency on the primary side. So all we need is that you will be making, now the question arises that how to transfer energy from primary to secondary. All we need, we will be having a primary winding here as well, that is represented by LP, and this is by making just a simple transformer. Here we will be able to transfer the energy from the primary side to that secondary side. Now what's behind that? Now this is the primary side, and we know that the resonant frequency or the oscillation frequency is 1 divided by 2 pi under root L C. So now on the primary side, what we are going to have, we will be having a positive DC voltage, and here a negative DC voltage, and then you will be having the IGBTs as a switch. Here you have IGBT, and here you have IGBT. IGBT is the and you know what is IGBT? IGBT comprises the benefits of BJT as well as the FET. And what is IGBT? You know from your previous knowledge of power electronics. Well, that's why we are using the IGBTs. And here what we have, we are going to supply it to the primary side, to the primary winding. So okay, let's make, and what we are going to here is that by using this IGBT, we are on the primary side, we are able to get this type of scare wave, and that scare wave and the frequency of that scare wave must be the frequency that must match with the frequency of this oscillation frequency. But things are not like that as you are looking here. I have just explained the concept. Now let's enter into the more detail. Before I proceed on, let's review the concept. Here we have the positive DC voltage, and here you have the negative DC voltage, and here you have two IGBTs, IGBT1 and IGBT2, and here you have a primary side, and on the primary side the waveform which we are generating here is by using the PWM. So what we are going to do, we will first turn this IGBT on, and in the next we will turn this IGBT on. So what happens that you are able to get such type of waveform here, and then the frequency of that waveform must match with the frequency of this inductor and capacitor on the secondary side, and there we go. Okay, now let's get more into detail. Let's making the circuit or the gate. Let's understand the gate driver circuit here. For a moment I am removing this, and let's have the actual IGBTs here. So here you have an IGBT1, and here you, let's say the voltage here is plus 170 volt, and then we have another IGBT which is connected here, and here you have the collector, the emitter and the base. again you have the collector, the emitter here, which is connected to minus 170 volts DC, and let's say this is the gate terminal, and here you have the gate. So what happens, you need to first turn this transistor on, and then you need to turn this transistor on. You don't want these both transistors to turn on, because if both of them will be turned on, what happens, there will be a massive short circuit between these two voltages and things will burn. But as here, one thing to note down here is that here you have the emitter, and the voltage here is, you can see the waveform here is of the very high frequency, because its oscillation frequency will be in the form of the kilohertz. So you have the very high frequency waveform here, and you know that the emitter is not grounded here, and emitter is in between, and emitter is connected to the collector. So we won't be using the low power gate driver IC. We will not be using the low power gate driver IC, because here you have the emitter and it is connected, and here we have a very high frequency here, high frequency waveform here. So your gate driver IC will get burned. So what should be here? Okay, we will be discussing this full bridge rectifier and the circuit later on. Okay, so which type of circuit which is used for this gate driver? Let's see and understand that. It's very easy. All you need is the proper gate driving arrangement. So what we have here, we will be using the 1:1 transformer here. This type of transformer we are going to use, and here you have the proper iron core 1:1 transformer, and here you have the primary winding. Now what we are going to do, we will connect this dotted end with this side, and it will be connected to this side. Here this is the dot and the dot. Here the dotted end is connected directly with the gate, but the dotted end of the second winding is not connected with the gate, rather it is connected with the emitter. And here you have the AC supply. Now what's happening is, here first this gate will on, and in the second attempt, in the upon second half, this transistor will turn on. So this is the basics of the proper gate driving circuit. Why these connections are inverted? Because we don't want both of these transistors to turn on, and this transformer 1:1 transformer is used to provide a proper isolation here, because low power gate driver IC will burn here because the waveform here is in the form of very high frequency waveform. So now this is what the gate driver circuit. Now your secondaries are isolated. Okay, so this is the basis of the gate driver IC. Now what's next? And one more thing, this is what the primary side. As we stated that our primary side also had the capacitor here. So what we are going to do, we are going to introduce a capacitor on the primary side as well. This is C1. Here we have plus 170 volt DC supply, and here we have minus 170 volt DC supply, and the waveform here is in the form of such type of waveform we are supplying here instead of the AC supply here, and this is the square waveform. Now what's next is that Now here we have a capacitor and here you have the inductor. We also willing to hit this capacitor and inductor on the primary side, which such a frequency, which is the oscillation frequency here, F oscillation on the primary side, and the oscillation frequency on the primary side must match with the oscillation frequency on the secondary side. So here the frequency of the waveform here, it must match with the oscillation frequency here, and in this way when this circuit will resonate, then that same frequency will be transferred to the next circuit, okay, and this will resonate as well. And since there is a transformation in voltage, so the voltage here will be in thousands of kilovolts, while the voltage here is just 5 to 10 kilovolt. So both are the resonating circuit, but they are working on the high frequency mutual inductance. So here is just the transformation. The resonant frequency of the secondary as well as the primary side are equal, and how we hit this inductor and capacitor with the right resonant frequency, by using this gate driver circuitry. We are going to supply here the frequency such that this frequency matches with the resonant frequency. So here is the basic working of the Tesla coil circuit. And one more thing which we are going to discuss is how we have created this plus 170 and minus 170 volts. So let us discuss that full bridge rectifier circuit, the modified circuit, in order to get this type of waveform. Okay, so this thing is clear. This is the basic circuit. Now in the rest part of my video, I am going to explain how this full bridge rectifier is used to generate plus 170 and minus 170 volt supply. Well, the other concepts of the Tesla coil circuit are explained here, and they are completed here. If you know how we generate plus 170 and minus 170 volt circuit, then it's okay, you can skip my rest part of the video. But if you don't know, then the rest part of video is for you. Let me remove this. And see how to generate positive 170 and minus 170. Okay, so let's first draw the circuit of the full bridge rectifier, which is very easy. You have 4 diodes in place. They are connected in this manner. They are connected here, and this diode is connected here, and this diode is connected with this diode, and here you supply the AC waveform. Let's say we have the 120 volts AC here. So, and then you have the ground reference here, and the waveform. I am also removing this circuit because I have explained you the details of that circuit, the working of that circuit. Okay, so the waveform which we obtain here is like in the form of the rippling DC. You have such type of waveform. You have the bumps like those, and if we add on the capacitor here, also known as the smoothing capacitor or the filter capacitor, what happens, the output becomes like this rectified DC. So what we are going to do, we are removing this ground reference from here and putting the ground reference here, okay, and also removing this capacitor from here. So which type of waveform we will be getting, let's see. At this point, with respect to the ground here, the waveform on this side, we will be getting the only the positive part of this waveform, and here this is the time axis, this is the voltage axis, and the peak will be around 170 volts because you get the peak voltage here, ideally 170 volt, and what you get here, the negative voltage, the negative parts of that voltage. Now what if we do, we just add the capacitors here, we add two capacitors here and provide the ground reference here as well, one here and one is here. So what we're gonna do is that we will obtain the plus 170 volts DC around the filtered DC here and minus 170 volts filtered DC here. So this is how you have obtained the plus 170 volt and minus 170 volt DC supply, and then we are here, as I told you, here you had the IGBTs, as you remember, we had the IGBTs, and then here what you have else, you had the driver circuit, as we just discussed. You have the transformers here, the 1:1 transformer, and okay, and what we had here, we are getting this type of waveform, the square waveform, plus 170 volts and minus 170 volt, and the frequency of this waveform is adjusted by the frequency of the transformer which is involved at the gate driver side. So this is how we get the plus 170 and minus 170 volt. So now I have explained each and every concept about the Tesla coils, the practical circuit. This is how your Tesla coil works, and you have the frequencies on the primary and secondary side, like they must be matched with each other. Now what are the applications? So let's discuss a few about the applications of this Tesla coil experiment. They are used in electric welding machine, it is also used there. Then it is also used as a spark plug ignition in engines. It is also used in cathode ray tubes, and also magicians use this. What they call them as magician, what they do, the output of the output voltage, you have a voltage of the kilovolts. What you do, you just place, or what they take near the light bulb near the Tesla coil, and they show you that this light bulb gets glow without actual connection, because here you have the high amount of the wireless power transfer. You can see them in labs or in different video lectures around the web, the different realistic experiments which people do with the Tesla coil, and such. The Tesla coil kits are available across the web. You can order those kits, you can play with the Tesla coil kit, and there are several other applications like the sound production in the air. The music is also produced through this Tesla coil in the air. Air acts as the big speaker. You can check out the detailed different experiments, the fun related experiments of the Tesla coil. Here in this part 2 I have explained each and every concept, the working, the full bridge rectifier, the practical circuit of the Tesla coil, which is well sufficient for you to take on your practical project related to the Tesla coil. Okay, so thanks for watching this video lecture. I will recommend you to subscribe this video lecture to this channel as well. Thank you.